Hello everyone. In this video, we will be further discussing about power amplifier. This video is released under Creative Commons Attributes 4.0 license used for technical purpose or educational purpose. Now, in the first video, we already described the basic amplifier terminology or basic amplifier terms. We also see the different amplifier classifications, and we are also discussing about power amplifier term. So in the previous video we already discussed about the basic configuration of amplifier with some classifications, the class A, class B and class C. Furthermore, we will be only discussing about class A amplifier. Every amplifier has a DC equivalent circuit and AC equivalent circuit. Because of this, it has two load lines, a DC load line and an AC load line. Now, for a small signal operation, the location of Q point is not a critical thing. But with a large signal amplifier, the Q point has to be at middle of the AC load line to get the maximum possible output swing. So before further discussions about this amplifier operations, first of all, we need to discuss about the how to plot a load line of the configuration. Now, over here, the configuration is shown to you is voltage divider bias common emitter amplifier. Now for given configurations, we need to discuss about how to draw a DC load line, and then after how to draw a AC load line, and then we are going to analyze the component of AC load line and DC load line. We decide the Q point location, and then we are further discussing about the operation of amplifier. So the first one is how to draw a DC load line, analysis. Now the crucial idea in getting the DC equivalent model is, first one is open all the coupling and bypass capacitor, because we know that capacitor is going to pass the DC signal while the capacitor is going to pass AC signal. So draw the DC equivalent circuit. Now we see that this is the basic configuration of VDB common emitter amplifier. Now this capacitor C1 and C2 is coupling capacitor, while C3 is bypass capacitor. Now by means of a DC analysis point of view, open all the capacitor and all the coupling and bypass capacitor, because capacitor is not allowing the DC component to pass, it only allow the AC component to pass. So I need to replace the capacitor C1, C2 and C3 in a open circuit way. So by this way you can replace the capacitor as an open mode for DC analysis. Now once I open the capacitor C1, once I open these two coupling capacitor C1 and C2 open, we can say that my source and load is bypassed. So only the DC model I have is, this is the only the DC model I have for voltage divided bias common emitter amplifier, where one DC source is there, R1, R2 collector resistor and emitter resistor is there, while the source and load is isolated from this configuration. Now to further plot a DC load line, I require to analyze this DC model. So this is my DC model. Now I require to write down a KVL equation in output branch. So if I'm going to write down a KVL equation in output branch, my equation is somewhat like this. VCC is equal to IC into RC plus VCE, that is a drop from collector to emitter, plus IE into RE. So I can write down the KVL equation from output side is VCC is equal to IC into RC plus VCE plus IE into RE. Now we know that IE is approximately IC, so I can replace this IE term with IC. My expression is fundamentally my expression is like the last expression. VCC is equal to VCE plus you can make the IC common, so IC times RC plus RE. So this is the KVL equation of my output branch. Now, if I require to draw a load line, then load line can be characterized by the 2 points. One you require to find out a cutoff point and other you require to find out a saturation point. Now, as this term like it is a cutoff point, the value of IC is 0. So if you require to find out a cutoff point for DC load line in this expression, you require to keep the IC 0. So to find out a cutoff point, keep the IC is equal to 0 in the above expression, that in turn produce VCC is equal to VCE. So this is called the VCE cutoff. So I can from this expression I can derive that VCE cutoff is equal to VCC. So this point is called my cutoff point. Now to find out a saturation point, I require to keep my VCE is equal to 0. So in this expression, in this generalized expression, I require to keep VC is equal to 0. If I kept VC is equal to 0, I can write down the term IC is equal to VCC upon RC plus RE. So this IC is nothing but IC saturation. So IC saturation will be derived as VCC upon RC plus RE. So from this analysis I got 2 points. One point is VCE cutoff, that value exactly equal to VCC, and other point is IC saturation. It can be calculated as VCC upon RC plus RE. So further moving, now we get two equation. VC cutoff is equal to VCC and IC saturation is equal to VCC upon RC plus RE. Now to draw a load line, we are characterized by the x-axis is VCE, y-axis is IC. So on the x-axis I require to plot VCE cutoff, that value is VCC. So that point is near about over here. So this point is called VCE cutoff, that value is exactly equal to VCC, and IC saturation point is somewhat over here. So that value is VCC upon RC plus RE. So cutoff point will be on x-axis, saturation point will be on y-axis. By interconnecting these 2 points with a straight line, this line is called a DC load line. So DC load line can be plotted with 2 points, cutoff point and saturation point. So this is the way by which we can plot a DC load line, where cutoff point is given by VCC while saturation point is given by VCC upon RC plus RE. So in general way we can say that the slope of DC load line is proportional to 1 upon RC plus RE. After formulating a DC load line, now we require to plot a AC load line as well for a same configuration, voltage divider bias, common emitter, amplifier. Now the crucial idea in getting the AC equivalent model is, first, short all the coupling and bypass capacitor, as this capacitor is going to allow the AC component to pass. Second, visualized the DC voltage source as ground. So VCC is my DC source for a given configuration, so that VCC source I require to make it ground, and then draw the AC equivalent circuit model. So if I replace this 3 terminology over here, then I replace the all coupling and bypass capacitor with short circuited, and I replace the DC source as an ground. So by looking at this configuration, now I can redraw this configuration in such a way that you can replace this entire circuit by this equivalent model, and this model is called your AC model, where if this BCC source is directly grounded, it is connected to the grounded. In alternative way, we say that R1 and R2 is in parallel. So I can replace these two component over here, where from the base to ground R1 and R2 will be in parallel. Along with this, we also agree with that RL, load register, and collector register also will be in parallel. So RL and RC both are in parallel, and a small IC amount of AC current is established in this branch. So effective resistance, this effective resistance is RL parallel RC, and this RE is absolutely having no any ideology. So that's why I can replace with all current is sufficiently passes from this short circuit way, so there is no any importance of RE register over here. So the rightmost this circuit diagram, this model is called a AC model. After deriving this model, now I required to write down a mathematical formulations to plot a AC load line. So this is the same model which we show in a previous slide. Now you write down the KVL equation in output branch. Now in this, all terminology will be replaced with small notations. So always I use through having a capital notations for DC analysis and small notations for AC analysis. So if I write down a KVL equation in output branch, I can write down small VCE is equal to minus IC times RC parallel RL. There is a small mistake over here. Instead of RE, you consider RL over here. This is a printing mistake is available. So kindly note that in that expression you write down small VCE is equal to minus IC times RC parallel RL. Now this minus will indicate the phase reversal of output signal with respect to input. So in amplifier configurations, we know that output signal is exactly 180 degree out of phase than input cycle. So this minus sign is having the evidence of the same. After writing down these expressions, where small rc is nothing but RC parallel RL. Kindly note that RE is RL actually. Now for further calculations, we know that actual amplifier configurations have two component, DC as well as AC component. So I can write down the total IC current. The total IC current is nothing but my AC IC current plus DC IC current. AC IC current will be indicated by small IC, plus DC IC current will be indicated by capital ICQ. So this is my total IC current. Similar way, my total VCE component is AC VCE component plus DC VCE component. DC component is generally indicated by ICQ and VCEQ. So from this one, if I put this two value in the above expression over here, this is my capital small VCE, that means this is my AC component. So AC component can be replaced with total VCE minus VCEQ. So keep this two value in above expression. I can write down these two component, capital VCE or the small VCE, that means AC VCE component is total VCE component minus VCQ. So you can replace this AC VCE component with total VCE minus VCQ is equal to minus small IC will be replaced at capital IC minus ICQ into ICRC parallel RL. Now that mistake has been corrected over here. Instead of RE, we require to consider RL over here. So this equation is already there in a correct way. So if I further simplify this expression, I can write down the entire expression by this way. IC is equal to ICQ plus VCEQ divided by RC parallel RL minus VCE divided by RC parallel RL. So this is the final expressions before computing the cutoff point and saturation point. So from the previous slide, I can take this equation in a as it is way. Now I require to find out the cutoff point and saturation point in a similar way we have computed with DC load line. So for in DC load line, to find out a cutoff point, I require to keep IC is equal to 0. So in to find out a cutoff point, keep IC is equal to 0. So that in turns produce VCE cutoff. That means if you keep the IC is equal to 0, the VCE cutoff is given by VCEQ. This VCE cutoff is given by VCEQ plus ICQ times RC parallel RL. So in this above expression, if you keep IC is equal to 0, you can derive the VC component, and that VC component is nothing but your VC cutoff value, which can be expressed by VCEQ plus ICQ times RC parallel RL. So this point A, capital A, that is the cutoff point for AC load line. To find out a saturation point, I require to keep VCE is equal to 0. So in the first expression, if you write down, if you keep the VCE is equal to 0, your expression IC, which is nothing but IC saturation point, is given by ICQ plus VCQ upon RC parallel RL. So this last expression is called a saturation point of your AC load line. So with this mathematical analysis, we finally concluded the two expression. One is the cutoff point for AC load line, which is given by VCE cutoff is equal to VCEQ plus ICQ times RC parallel RL. And second expression is the IC saturations is given by ICQ plus VCQ upon RC plus RL. So this point A and point B is my AC load line intersection point. So with a similar way, we can plot these two components. This expression is remain same like earlier. Other expression is remain same like earlier. We plot the cutoff point on x-axis. That value is VCE cutoff. The saturation point will be on y-axis. That value is ICQ. So the value of this point is given by VCEQ plus ICQ times RC parallel RL, and the value of saturation point will be given by ICQ plus VCQ divided by RC parallel RL. Now we know that from this expression we can comment that the slope of AC load line is proportional to 1 upon RC parallel RL. So from this DC load line, we already have concluded that the slope of DC load line is proportional to 1 upon RC plus RE, while in case of AC load line, we concluded that the slope of AC load line is proportional to 1 upon RC parallel RL. So finally, we concluded that till point we studied about DC analysis and AC analysis. So from the DC analysis, now we concluded the 2 point VC cutoff is given by VCC. Let me indicate this point as capital A. IC saturation is given by VCC upon RC plus RE. Let me indicate this point as capital B. So capital A, that is the cutoff point for DC load line, while capital B is known as saturation point of DC load line. Similar way, we also know about a AC load line intersection point, where VC cutoff point will be given as VCEQ plus ICQ times RC parallel RL. Let me indicate this point as capital C. And IC saturation is given by ICQ plus VCQ divided by RC parallel RL. Let me indicate this point as capital D. So now we know that capital A and capital B, that is cutoff and saturation intersection point of DC load line, while capital C and capital D, that is cutoff and saturation point of AC load line. Now let me combine these two load line on a same axis. So my VCE versus IC characteristics, this is my DC load line which having an intersection point capital A and capital B. Capital A, that is cutoff point, which is given by the value is given by VCC, while capital B is saturation point. This point can be evaluated as VCC upon RC plus RE. Similar way, the AC load line also can be drawn like this, which intersection point is C and D. This C can be evaluated as VCEQ plus ICQ times RC parallel RL, plus this point D is evaluated as ICQ plus VCQ divided by RC plus RE. Now we compare this one where this AC load line and DC load line is intersect. This point is known as Q point. Now from this Q point, if I project this Q point on a x-axis, this component is known as VCEQ. Similar way, if I project this point on a y-axis, this point is known as ICQ. So this VCEQ and ICQ is my DC component. So once the AC load line and DC load line will intersect, this intersection will leads to an Q point. This Q point will be projected on x-axis. This component is known as VCQ, and this Q point will be projected on y-axis, and this component is known as ICQ. Now let me correlate this value with the previously derived expression. This point C, that is a cutoff point for AC load line, will be calculated as VCQ plus ICQ times RC parallel RL. So this component will be analyzed by this way. Up to origin to this point, this much of point, that is your component VCEQ. The remaining component from VCQ to intersection point C, that component is known as ICQ times RC parallel RL. So your total cutoff point, AC cutoff, will be calculated as the addition of these two components VCEQ plus ICQ times RC parallel RL. Similar way, the saturation point can also be realized like this way. This much of component is the constant component ICQ plus VCQ divided by RC plus RC parallel RL. So this component D can be evaluated, this much of value is evaluated as ICQ plus VCQ divided by RC parallel RL. For the same way, the DC component can also be evaluated by this way. For DC load line, this component A value is exactly equal to VCC, but this component now can be realized by this way. This much of component for DC load line, this the value of capital A is VCC, but we know that from origin to the Q point intersection, this much of component is VCQ. This much of component is VCQ. So from this point to the intersection A, the remaining component, this remaining component will be evaluated as ICQ times RC plus RE. Because from the DC analysis, we have write down the KVL equation for output branch, and we know that VCE is equal to nothing but that is VCE plus ICQ times RC plus RE. So this much of remaining component can be known as ICQ times RC plus RE. Right? So for AC load line point of view, the remaining component from VCQ to the intersection point C, this component is known as ICQ times RC parallel RL, and for DC load line point of view, this much of component is ICQ times RC plus RE. So this is the only difference, only basic difference in AC load line calculation and DC load line calculation. This component is common for both the point of view. Similar way, on a y-axis, we can calculate this DC component. This component, the point B can be evaluated at this much of component is ICQ, and the remaining component is VCEQ divided by RC plus RE. So if you thoroughly understand this diagram, the rest of the analysis throughout the chapter is quite easy for you. So let me summarize this entire thing. For AC load line and DC load line, the DC load line has intersection point capital A and capital B. Capital A intersection point is evaluated exactly like the VCC, but alternate way you can also write down this. If you don't know the VCC and if you have the VCE component, VCQ component and ICQ component, then also you can get to know about the value of cutoff intersection point for DC load line. So this value is given by VCEQ plus ICQ times RC plus RE. For AC cutoff point will be evaluated as VCEQ plus ICQ times RC parallel RL. Similar way, the DC load line saturation point is can be calculated as ICQ times ICQ plus VCEQ divided by RC plus RE, and the AC load line saturation point is given as ICQ plus VCQ divided by RC plus RE. Now in another way, we already calculate this point B. The value of point B also can be calculated as the value of point B is also can be calculated as VCC upon RC plus RE. Of course, it is indicated somewhat higher over here. This is by mistake, will be the position will be shifted over here, but the point alternative way, the point B can be calculated as VCC upon RC plus RE. But if you don't know this value of VCC at both this end, the alternative way you can calculate this intersection point if you know the component VCEQ and ICQ. So I request you carefully look in this diagram. This diagram at later stage will lot more helping you while calculating the example. And from this we already derived that the slope of DC load line is directly proportional to 1 upon RC plus RE, while the slope of AC load line is directly proportional to 1 upon RC parallel RL. So whenever we talked about a DC model or DC load line, always the RC plus RE will be in picture. And whenever we talked about a AC load line point, or AC load line analysis, always the RC parallel RL will be in picture, because for AC load line point of view, generally we make the bypass capacitor short circuited, which will absolute the emitter resistor, while in case of DC load line we are keeping this capacitor open, and that's why source and load are isolated. So load resistor is never came into the picture of DC load line, while the emitter resistor will never came into the picture of AC load line. Thank you very much.